Good morning. Howdy. Good morning. Salutations. Worded? Oh my gosh. You ever just wake up with a headache? I've got a headache this morning. Okay. I'm going to go ahead and get started. What's up, Courtney? She pops in again. Okay, let's get started. So, we were talking about circular motion. So today we're going to do some different circular motion problems. So the first type of problem that we're going to discuss today is called a banked turn. Okay. So what does a banked turn look like? So we can draw a banked turn from a top view. So from a top view, it just looks like a regular circular motion. Okay. So let's just go ahead and consider a car in a banked turn. So here's the car. It's in a banked turn. Okay. The car's velocity points tangent to the circle, and the car's acceleration points towards the center of the circle. By the way, the radius of this circle we will call big R. Okay. Now let's do a sort of rear view of the car. Okay. So it is a banked turn, and it is a very steep turn. Okay. So we're going to say it's banked at let's say it's banked at an angle of 60 degrees. Okay. Hang on one second. I just want to make sure that this problem works out. And here's the car. Sort of a rear view of the car. Okay. So the car is traveling into the page here because this is a rear view of it. Okay. So the velocity is into the page. The acceleration is towards the center of the circle, which is right in that direction. Okay. So the car swings around, and if it was on the other side, here's the other side of the bank, like this. Okay. And so the car goes into the page, it comes around, and on this side it would be going out of the page, its velocity. The radius of the circle would be this distance right here. So I hope that makes sense, that you can visualize this problem. Now, tires have a coefficient of static friction with the road and a coefficient of kinetic friction. Okay, if the car is operating properly, it should be static friction, because if it's kinetic friction, that means that the tires are spinning on the road. You're peeling out. So we're gonna consider the case of static friction, and static friction. The coefficient of static friction is just going to be 1.0. All right. We're going to say that the car has a mass m. All right. Now, what would happen if the car is trying to go too fast around this corner? What would happen is it would slide up the edge of the turn, okay? It would slide up, 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 and it would fall over the top, okay? So that's what would happen if the car was going too fast. If the car is going too slow, it's going to slide inward towards, and it's going to fall into here, okay? So my question is, oh, I better give the radius of the turn too. Let's say the radius of the turn is 20 meters, all right? My question is, what is the minimum speed the car must have to do the circle without sliding inward? Okay? And this is important. It's sliding inward. Okay? So let's do a free body diagram. What are the forces on the car at this particular instant? All right? So we have normal force is going perpendicular to the incline, F sub n. We have weight force, mg, which is vertical. And then we have friction, okay? Now, if the car is about to slide inward, then friction has to point outward. So tangent to the incline, but outward. So friction is going in this direction. This should be a right angle here. All right, does everyone understand that? The problem that you guys are going to be doing in the homework, in the quiz for today, is going to have what is the maximum speed that the car can have in order to not slide outward. And if the car is about to slide outward, then friction would be pointed inward. You get what I'm saying? So for your homework, you're going to have to reverse the direction of friction compared to me. Now, if you do the trigonometry here, you will find that this angle is 60 degrees. And you will find that this angle is 60 degrees. Okay? So why is that? Well, if we think about friction and normal force, if this were a flat incline, then friction would point straight up and normal force would point to the right. And then what are we doing in that flat incline? We're rotating it by 60 degrees. So this vector, which represents friction, gets rotated up by 60 degrees. And this vector, which represents normal force, gets rotated to the left by 60 degrees. Okay? So that tells you why these are 60-degree angles. So we can take this and we can write it. So the sine of 60 is 0.87. Okay? And the cosine of 60 is 0.5. Okay? So what I can do is I can write this with all the forces being vertical or all the forces being horizontal. So this upward is going to be F cosine of 60. So I've got an upward force of friction times, that's F sine of 60. Friction times 0.87. The upward component of the normal force is adjacent to this angle, so that's going to be normal force times cosine of 60. So this is 0.5 normal force. And then I have mg going downward. I have a leftward normal force, which is F sub n times sine of 60. So 0.87 F sub n is going to the left. And then I have friction times cosine of 60 going to the right. Okay? Hang on one second. I gotta make sure. Okay. Cool. So that's going to be 0.5 times friction is going to the right. Now, what direction is the acceleration? Well, the acceleration is pointed towards the center of the circle, which is to the left in this case. All right. So let's go ahead and do Newton's second law in the vertical direction. So I have net force in the y direction equals m times the acceleration in the y direction. Well, what is the acceleration in the y direction? The car is not sliding up and down, okay, because it's not sliding inward. So that means that the acceleration in the y direction is 0, okay? And so the net force in the y direction is up forces minus down forces. So I have 0.5 F sub n plus friction times 0.87 minus mg equals 0. Okay. Now remember that this is static friction, and static friction is going to be maxed out because if you go any slower, it's going to slide inward. So friction is working as hard as it can to keep the car going. So the maximum static friction is mu sub s times normal force. The coefficient of static friction is 1.0. So basically, static friction max is going to be equal to normal force in this case. They wouldn't be equal if the coefficient of static friction wasn't 1. Okay? So I have 0.5 F sub n plus 0.87 F sub n equals mg. Okay? Combining those, this is 1.37 F sub n equals m times 10, because gravity is 10. All right? And so dividing both sides by 1.37 gives us 7.3. The normal force is 7.3 times the mass. Okay? The mass is going to cancel out. That's why I haven't given you the mass yet. Okay, so we have that. Now let's do Newton's second law in the x direction. I'm going to take leftward to be positive. Okay, so the net force in the x direction is 0.87 to the left. And then 0.5 to the right. Now, notice how I didn't write 0.5 friction. I wrote 0.5 F sub n because for this particular problem, friction is going to be equal to the normal force. Okay? And then I have m times the acceleration. It's moving in a circle, so I will use the centripetal acceleration equation, v squared over r. Okay, so plugging this in, or going to the next line, I have 0.37 f sub n equals m times v squared over 20, because 20 is the radius of the circle. And then the normal force is 7.3 times the mass. So I can see that the masses cancel out. So all cars are going to have the same minimum speed, all right, as long as they have the same coefficient of static friction. And so what I get is that the speed is the square root of 20 times 0.37 times 7.3. And we get, it has to go at least 7.35 meters per second. If it goes less than that, it will slide into the center. Okay? So, this is an example of what's called a banked turn problem. So for banked turn problems, you might have friction, you might have normal force, and, all right? You might have friction, you might have normal force. And they're going at angles. Okay, let's do one more bank turn example that I think is nifty. And that is for an airplane. And we are going to use the more realistic model of the drag force, or of lift. Okay, so the lift force on an airplane is going to equal a constant times the speed squared. Okay, this constant depends on the density of the air, it depends on the shape of the wings, and actually it depends on the speed of the airplane as well. But so an airplane can change its lift constant by adjusting the flaps. Okay, an airplane also has a drag force, which you can think about this as C1, and the drag force obeys the same law but with a different constant. And so basically what happens is if you want to generate more lift, you turn the flaps, you turn the flaps on the airplane, and that will increase lift. But it also increases drag. So the more, if you want to increase C1, you also increase C2, which means the engine has to work harder against drag force. Okay, so these two are interconnected. But for this problem, we're not going to worry about the drag force. Okay, and the way that the lift force works is it points perpendicular to the wings of the airplane. So let's suppose we're looking at a top view of the airplane. The airplane's going in a circle. Okay, here's the airplane. Here's its wings. It's like that. Okay. If we look at a rear view of the airplane, okay. If we look at a rear view of the airplane, it's going to look like this. So the airplane is banked. All right. So here's the tail of the airplane. It's banked by some angle theta. So that means that the lift force is rotated by an angle theta, because the lift force points perpendicular to the wings. All right. The radius of this circle is big R. And then the weight force on the airplane points down. So which way does the drag force point? Well, if the airplane is going around this way, the the drag force is pointing out of the page towards you guys, and the thrust force of the airplane is pointing into the page. And those two are balancing each other so that the airplane is executing this circle at a constant rate. Okay? All right. So, what do we have here? Well, the net force in the y direction has to equal 0. Why? Because the airplane is undergoing a level circle. Okay? So it's going in a horizontal circle. So what are the vertical forces? We have basically we have F sub L cosine of theta going up, and we have mg going down, and those have to balance out. So that means that, and the lift force is, of course, a constant times v squared. So this is one of the equations for an airplane that's going in a circle. All right. The other equation is the equation in the x direction, which is mv squared over r. In the x direction, the net force is lift times sine of theta. So we have cv squared times sine of theta equals mv squared over r. So this is our second equation. Interestingly, you can see that the velocity squared cancels in this equation. So based on these two equations, I love these two equations, okay? Because they allow you to predict the radius of the circle that the airplane will turn in, and how that depends on how much the airplane turns. The more the airplane turns, the sharper the turn it goes in. Okay, so I could talk about it, but I kind of want you guys to discover and play around with these equations in the quiz today. So I'm going to leave it, and I'm not going to go and do a detailed discussion. Maybe I'll talk about it next time. All right, so I just wanted to do that because I expect that problem will challenge you. So the second topic for today is the topic of vertical circles. Okay. So we have been discussing so far horizontal circles. So they're circles that are in the horizontal plane. A vertical circle is one that is going around like this. Okay. So if we think about a vertical circle, you could be at the bottom of the circle. So these are all side views. Okay, so for example, what if we had a car at the bottom of a circle, like this, and then you have a normal force below you. So this would be like a car that goes into a ravine or something. You could have a car that's at the top of a hill, like this. All right. So that would be an example of a vertical circle. Or you could have something like a skateboarder who's at the top of a circle and upside down. So these are some different scenarios I want to consider. So maybe the velocity is this way. So what are the forces in each case? All right, in this case, we have a weight force going down. Keep in mind, this is a vertical circle. So if you have a horizontal circle, the weight force points perpendicular to the circle because the circle's in this plane and the weight force is down. If you have a vertical circle, like that's going around like this, then the weight force points down. Okay, so that's what makes vertical circles somewhat challenging. like if we think about this problem, the weight force on the airplane from this perspective points into the page. So it's the weight force in some sense is not affecting the circular motion directly. Okay, but here it is. And then you have a floor below you. So there's a normal force going upward. Okay. Here, again, you have the floor below you. So the normal force points upward and the weight force points downward. Here, you have a, here you have the floor is above you. So that means that the normal force points downward and the weight force points downward. Okay? So you can see that in vertical circles, you have to be really careful about the directions of normal forces and weight forces. Okay? You also have to be really careful about the direction of the acceleration, because here's the center of the circle, here's the center of the circle, here's the center of the circle here. So notice how the center of the circle may be above you or below you. And the reason that that's important is because the centripetal acceleration always points towards the center of the circle. Okay? So in this example, the acceleration points straight up because the center of the circle is above. In this example, the centripetal acceleration points straight down because the center of the circle is below. Here, it also points straight down because the center of the circle is below. Okay? By the way, you would never be asked a circular motion problem that's a vertical circle where it is not at the top or the bottom of the vertical circle. Okay, if it was something where it was like right here, that becomes significantly more complicated because you have a normal force going this way and you'd have a weight force going that way. So it gets more complicated because they become, so we won't consider that. So let me write out Newton's second law in each case. Okay. So that's Newton's second law. And we're going to use the fact that up forces are positive and down forces are negative. Okay. And up accelerations are positive and down accelerations are negative. So the net force in this case is going to be up force minus down force. N minus mg. And that equals ma. The acceleration is upward, so it's a plus v squared over r. So this is Newton's second law in this case. In this case, we have up force minus down force, N minus mg, equals mass times the acceleration. But here the acceleration is negative, it's downward. So we have negative v squared over r. All right. Here we have both of these forces are downward. So our net force is going to be minus n minus mg equals m times the acceleration. The acceleration is also downward, so we have minus v squared over r. So notice how in each of these cases the signs are switching around. Okay, so the toughest part about vertical circles is getting the signs of all of these terms correct. All right. So I'm not even going to do an example with it. Well, I'm going to do an example, but okay. So my point is that the mathematics is really simple, but you just got to get the signs right. Okay. One type of problem that you may be asked to solve is one where you have something at the top of a circle. Okay. And what happens if you're at the top of this circle and you were going too fast? You would actually lose contact with the hill at the top of the circle. If you go over the top of a hill too fast, you will actually fly into the air. Okay? So a question might be, how fast is too fast? What is the maximum speed you can have without losing contact? Okay? All right? What about in this one? What happens if you go too slow? What if you're a skateboarder and you go too slow over the top of this loop? You would actually fall out of the loop. So for this one, you could ask the question, well, what is the minimum speed that you have to have in order to not lose contact? All right? And so there's this type of problem where it's like, well, you're going to lose contact. And anytime you lose contact, that means that the normal force is now equal to 0. So losing contact means normal force is equal to 0. All right? So burn that into your brain. Let's do an example. And this example is a rope swing. Can you lose contact if you are going too slow up a hill? No, you can't. It's only once you go over the top. All right. So, it would either be this scenario or this scenario. Here you have to have a normal force that's not equal to 0. If you solve for the normal force here, you get N equals mg plus mv squared over r. So the normal force is you're adding two positive numbers together. You can lose contact at any point where the normal force is equal to 0. Okay, so yeah, so you actually could lose contact right here going down the hill, for example. But we're only going to consider top of the hill or bottom of a ravine. So what if you have a rope swing and you have a person who is like this, and here's the rope, all right, and they swing down like this. So the rope goes vertical here. All right. Let's say that the rope is 11 meters long. And let's say that the mass of the person is 50 kilograms. All right. I remember one time when I was a kid, I used to play baseball. And we went to Canada to play a baseball tournament. And we stayed at this camp. And okay, so we're staying at this camp, the baseball team, and the owners of the camp had a son, okay, and it was like late at night, and the son, so I had kind of like made friends with the son of the camp owners, so he knocks on my door like in the middle of the night, and he's like, "Hey, you want to go swimming in this lake?" He's like, "You guys should come swimming. Let's go swimming." And think about this. I'm 13 years old or something like that, and I'm like, "Yeah, let's go swimming at midnight in this lake." And so I get the rest of the team, and we go out to this lake. It's dark. There's a rope swing. So we were doing rope swings into a lake, and I had no clue how deep the lake was. Like the lake could have been really deep or really shallow, but we just trusted the guy. We're doing rope swings, and we're just getting flung up into the air into the lake, and it's dark. We have no clue what's going on. Someone could have drowned. But it was just one of those memories that just sticks with me, And then the next day, when it was the daytime, all of the adults also did the rope swing. And I also have a vivid memory of one of the moms did the rope swing. And as she was doing the rope swing at the lowest point, she couldn't hold on to the rope. And so she just went and then let go like right here and just like slammed into the dirt. I can picture it. It's like a photographic memory of her just going splat. So, anyways, good times. So my question is, what is the tension in the rope at the lowest point? All right, that's the long way of getting to this problem. So here's what we're going to do. We're going to use energy to get the speed right here. Okay? So if we think about it, because this person is moving in a quarter circle, essentially, the amount that they drop is equal to the radius of the circle. So we have initial energy equals final energy. All right? So initially they have mgr of gravitational potential energy because they're one radius higher than where they end up. And then they end up with kinetic energy 1/2 mv squared. So the m's cancel out. All right? And what we get is v squared is equal to 2 times g times r. I'm actually going to just leave it as v squared, and you'll see why in a second. So that says that v squared is equal to 2 times 10 times 11. So that's what, 220 is v squared. Okay? Now, we're going to use the fact that this is a vertical circle. So what's happening at the bottom here? We have tension pointed upward. We have weight force going downward. And the acceleration is up towards the center of the circle. So my Newton's second law at the lowest point is up forces minus down forces equals m times positive v squared over r, because the acceleration is upward. So I have tension minus mg, so mg would be 50 times 10, so 500, equals 50 times, and notice how the equation has v squared. So that is why I didn't even bother taking the square root of that, because then I would just square it again. So v squared is 220 over 11, and I can solve for the tension in the rope. Uh, 1,500 newtons. All right. So what if you had a rope, for example, that could only withstand 1,000 newtons? Then that rope is going to break, and this person is going to go splat. All right. So that's my lesson for today. I will see you in the Zoom room.